For centuries, physics operated under a strict set of rules. Matter existed as localized, solid particles that occupied a specific point in space, while energy traveled outward as spreading, continuous waves. These two models of reality were considered mutually exclusive extremes. A rock was a rock, and a wave was a wave. Central mathematical rule. You take Planck's constant and divide it by an object's momentum. The resulting number gives you that physical object's actual wavelength. But applying this math creates an immediate mechanical problem. Standard waves propagate endlessly through space. If an electron truly behaves as a continuous wave, its physical mass would have to be smeared across the entire universe. We know that contradicts reality, because every time we run an experiment, we measure the electron in one discrete, localized spot. To explain how something can be both an infinite wave and a localized point, physicists needed a completely new mathematical blueprint. This starting point is a single, uniform sine wave, repeating endlessly. It has a precise frequency, giving an exact momentum. But stretching infinitely, we have zero information about position. Watch when we introduce a second wave with a slightly different frequency. Superposition takes over, warping the uniform shape into uneven crusts and troughs. Stacking dozens of different waves, they destructively interfere almost everywhere, leaving only one concentrated, isolated spike. Physicists call this localized peak a wave packet. This concentrated geometry is the true mathematical architecture of a quantum particle. Look closely at how it moves. The individual ripples fluttering inside the packet travel at what is called the phase velocity, but the overall peak itself marches forward at a different speed, called the group velocity. That group velocity happens to match the exact speed of a classical moving particle. By layering multiple infinite waves together, the math creates a localized shape that perfectly mimics a solid object traveling through space. In 1927, researchers moved this theory out of the math equations and into the physical world. The Davison-Germer experiment was set up to test whether solid matter genuinely exhibits this wave behavior. This schematic shows the setup. They fired a focused beam of accelerated electrons into the atomic grid of a nickel crystal. If electrons were microscopic billiard balls, they would ricochet in a standard scatter pattern. Instead, the detector recorded a massive intensity spike exactly at a 50-degree angle. This is the mathematical signature of an interference pattern. The diffraction pattern provided undeniable physical proof. The electrons were not bouncing off the nickel as solid spheres. They were physically interfering with each other as waves. But if an electron is a wave packet moving through a vacuum, we have to ask, what physical substance is actually waving? Max Born and Erwin Schrödinger realized that the wave is not made of water or air or any physical material at all. It is purely a mathematical wave of probability. Looking at this plot, the vertical axis represents probability. The highest peak of our localized wave packet is simply the coordinate where the particle has the highest probability of being found when an observer actually measures it. This probabilistic geometry directly connects to Werner Heisenberg and the mechanics of his famous uncertainty principle. In physics, you face a mechanical trade-off. To make a narrow wave packet and know a particle's position, you must stack infinite frequencies together, destroying your knowledge of momentum. Reverse the process. Using one frequency gives perfect momentum, but forces the wave packet to stretch infinitely, making position impossible to determine. At the microscopic level, reality isn't built out of hard spheres. The physical world is an intricate mathematical dance of overlapping probabilities, all stacked together to trick us into seeing a solid universe. For centuries, physics operated under a strict set of rules. Matter existed as localized, solid particles that occupied a specific point in space.